In the spring of 2018, two scientists sat together in a small office at the Goddard Institute for Space Studies in New York City. One was Gavin Schmidt, a climate modeler who had spent decades simulating Earth's atmosphere across geological epochs. The other was Adam Frank, an astrophysicist whose work centered on the search for life beyond our world. They were not fringe theorists. They held positions at NASA and the University of Rochester. Their publications had appeared in the most respected journals. And yet the question they posed that afternoon carried an unsettling weight, a quiet disturbance that would ripple outward through the scientific community in the months and years to come. They asked, if an industrial civilization had existed on Earth millions of years before humans, would we be able to detect it in the geological record? And if the answer was no, what did that mean for our understanding of time, of intelligence, of the narrative we tell ourselves about being first? This question was not born from idle curiosity. It emerged from a practical problem in astrobiology. When we search for technological civilizations elsewhere in the universe, we assume certain signatures, certain marks that intelligence leaves upon a planet. We look for atmospheric changes, for chemical imbalances that suggest machinery and combustion and the deliberate manipulation of matter. But how long do these signatures persist? If a civilization rises and falls within a geologically brief span, say 10,000 years or even 100,000 years, does it leave a mark that endures for millions or hundreds of millions of years after its collapse? To answer this, Schmidt and Frank realized they needed to look inward to examine Earth itself as a test case. If we could not detect our own civilization after it vanished in a deep time, how could we expect to detect others across the galaxy? They called their inquiry the Silurian Hypothesis, a name borrowed from a science fiction television series in which an ancient reptilian species had ruled Earth long before mammals evolved. The name was playful, but the hypothesis was not. It did not claim that such civilizations had existed. It made no argument for lost empires or forgotten technologies buried beneath our feet. Instead, it posed a thought experiment, rigorous and methodical. It asked what traces an industrial society would leave in the geological record, and whether those traces could be distinguished from natural processes after tens or hundreds of millions of years had passed. The answer they arrived at was both simple and disturbing. Most evidence, they concluded, would vanish, and what remained would be ambiguous, easily attributed to volcanism or asteroid impacts or other planetary upheavals that leave similar scars. To understand why this is so requires a confrontation with deep time, a concept that challenges the intuitions built into human perception. We live our lives in decades. Our recorded history spans mere millennia. Even our species, Homo sapiens, has walked the Earth for only 300,000 years, a duration that feels vast when measured against individual human experience, but is vanishingly brief when set against the 4.5 billion year history of the planet. Geological time operates on scales that render human civilization nearly invisible. The entire span from the construction of the first cities to the present day would compress, in the rock record, into a layer of sediment thinner than a fingernail. Most of human history would not appear at all, because most of the surface of the Earth is not currently accumulating sediment that will become rock. Erosion dominates. Mountains wear away. Coastlines retreat. Rivers carve and fill and carve again. The ground beneath our feet is not a passive recorder of events, but an active system, constantly destroying its own memory. The geological record is not a book with every page intact. It is a book with most of its pages torn out, burned, shuffled, written over, and then torn out again. Geologists estimate that only a tiny fraction of Earth's surface at any given moment is undergoing deposition in environments where sediments will be preserved long enough to lithify into rock. River deltas, lake beds, shallow ocean basins, these are the places where the past has a chance of being written down. But even there, the record is intermittent. Sea levels rise and fall. Climate shifts. What was once a lake bed becomes a desert, and the sediments blow away. What was once a seabed is thrust upward by tectonic forces, exposed to wind and rain, and eroded back into dust. The rare sediments that do survive, that harden into stone and persist for millions of years, represent only brief snapshots, isolated moments separated by vast, unrecorded intervals. This incompleteness is not a failure of geology. It is a fundamental characteristic of the planet. Earth is dynamic. Its surface is carved into plates that drift across the mantle, colliding and grinding and pulling apart. Oceanic crust, where much of the planet's sediment accumulates, is recycled into the mantle through subduction zones, swallowed back into the depths every few 100 million years. The oldest oceanic crust on Earth today is less than 200 million years old. Everything older has been destroyed, melted, reabsorbed into the convecting interior. Continental crust persists longer, but even it is constantly reworked. Mountains rise and erode. Basins fill and are uplifted. Ancient rocks are buried, heated, metamorphosed, their original structures and compositions altered beyond recognition. The Earth is a machine that devours its own history. Now consider what this means for the preservation of civilization. Cities are built on the surface, the least stable part of the planet. They are made of materials, concrete and steel and glass and plastic, that are not designed to endure geological time. They are designed to last decades, perhaps centuries if maintained. But without maintenance, without the constant attention of their builders, they begin to decay almost immediately. Steel rusts. Concrete cracks and crumbles as water seeps in and freezes and expands. Glass shatters. Plastics photodegrade in sunlight, breaking into smaller and smaller fragments. Within a few centuries of abandonment, even the largest structures begin to collapse. Within a few millennia, they are reduced to rubble, scattered and buried by soil and vegetation. Within a few tens of thousands of years, they are weathered down to unrecognizable mounds, indistinguishable from natural landforms to the untrained eye. But surely, one might object, some trace would remain. Surely the sheer quantity of material we have moved, the trillions of tons of earth excavated, the metals refined, the chemicals synthesized would leave some permanent mark. And this is true to a point. But the question is not whether any trace would remain. The question is whether that trace would be recognizable and distinguishable from natural processes after millions of years. And here the answer becomes less certain. Take metals, for example. Human civilization has extracted vast quantities of copper, iron, aluminum, gold, rare earth elements from the crust. We have concentrated these metals, refined them, shaped them into tools and machines, and wires and coins. When our cities fall and our machines corrode, these metals do not vanish. They oxidize, they dissolve, they are transported by water and wind, and eventually they are redeposited elsewhere, often in forms that resemble natural or bodies. A future geologist examining sediments from our era might find elevated concentrations of certain metals, but would they recognize this as artificial? Or would they interpret it as a natural enrichment, perhaps the result of hydrothermal activity or the weathering of a nearby mineralized zone? The distinction is not always clear. Plastics present a more intriguing case. These materials, polymers synthesized from petroleum, are genuinely novel, absent from Earth's surface before the 20th century. They degrade slowly, and fragments of plastic are now found in sediments around the world, particularly in marine environments. Some geologists have suggested that a future geological survey would identify a thin plastic-rich layer corresponding to the mid-20th century onward, a marker horizon dubbed the Anthropocene. But plastics do eventually break down. Ultraviolet radiation, heat, microbial action, mechanical abrasion, all of these processes fragment and degrade polymers over time. The largest pieces disappear first, leaving behind microplastics, then nanoplastics, then molecular residues that become increasingly difficult to distinguish from natural organic compounds. Over millions of years, even these residues may be altered beyond recognition, transformed by heat and pressure and chemical reaction into substances indistinguishable from other carbon-bearing minerals. Radioactive isotopes offer another potential signature. Nuclear weapons testing in the mid-20th century scattered artificial radionuclides, particularly plutonium-239 and cesium-137, across the globe. These isotopes do not occur naturally in significant quantities, and their presence in sediment layers is a clear marker of human activity. But radioactive isotopes decay. Cesium-137 has a half-life of about 30 years. After a few centuries, it is effectively undetectable. Plutonium-239 has a much longer half-life, over 24,000 years, but even this is geologically brief. After a few 100,000 years, the plutonium signal fades into the background. A civilization that rose and fell millions of years ago, even if it developed nuclear technology, would leave no detectable radioactive signature today. So what signatures might persist? Schmidt and Frank turned to chemistry, specifically to the carbon cycle. Industrial civilizations burned fossil fuels, releasing carbon dioxide into the atmosphere. But this carbon has a distinctive isotopic composition. Fossil fuels are derived from ancient organic matter, plants and plankton that lived millions of years ago. These organisms preferentially incorporated the lighter isotope of carbon, carbon-12, over the heavier isotope, carbon-13, during photosynthesis. As a result, fossil fuels are depleted in carbon-13 relative to the carbon in the atmosphere or in rocks like limestone. When we burn coal and oil and natural gas, we release this isotopically light carbon, creating a measurable shift in the carbon isotope ratio of the atmosphere, the oceans, and the sediments accumulating at the time. This shift, known as a carbon isotope excursion, is detectable in the geological record. It appears as a sudden change in the ratio of carbon-13 to carbon-12 in carbonate minerals, in organic matter, in the shells of marine organisms. The excursion caused by modern industrial activity is clear and well documented, appearing in sediments and ice cores from the past 2 centuries. But here is the critical question. Would this signal remain detectable after millions of years? And if it did, could it be distinguished from natural carbon isotope excursions caused by volcanic eruptions, methane releases, or other planetary events? The geological record contains numerous carbon isotope excursions. Some are small, barely perceptible shifts. Others are dramatic, profound changes that coincide with mass extinctions and climate upheavals. These excursions occurred long before humans existed, long before any mammal or bird or dinosaur walked the Earth. They are typically attributed to natural causes, massive volcanic eruptions that release carbon dioxide from deep within the Earth, the sudden destabilization of methane hydrates buried in ocean sediments, the impact of asteroids or comets. These explanations are plausible, supported by evidence, and consistent with our understanding of planetary processes. But they're not always complete. Some excursions remain poorly explained. The timing is uncertain. The source of the carbon is ambiguous. The mechanisms that triggered the change are debated. One of the most studied events is the Paleocene-Eocene thermal maximum, which occurred approximately 56 million years ago. This was a period of rapid global warming, during which temperatures rose by 5 to 8 degrees Celsius over a few thousand years. The warming was accompanied by a dramatic carbon isotope excursion, a sudden influx of isotopically light carbon into the atmosphere and oceans. The event lasted for about 200,000 years before the climate system gradually returned to its previous state. The consequences were severe. Ocean acidity increased as carbon dioxide dissolved into seawater. Deep-sea organisms, particularly those with calcium carbonate shells, suffered widespread extinction. Ecosystems on land and in the oceans were disrupted and reorganized. New species appeared. Old ones vanished. The prevailing explanation for the Paleocene thermal maximum is that volcanic activity in the North Atlantic, associated with the opening of the ocean basin between Greenland and Europe, triggered the release of methane hydrates from the seafloor. Methane is a potent greenhouse gas, and its oxidation in the atmosphere produces carbon dioxide, amplifying the warming. This explanation is widely accepted, but it is not without difficulties. The exact timing of the volcanic activity relative to the onset of the warming is uncertain. The amount of methane required to produce the observed carbon isotope excursion is enormous, and it is not entirely clear where it all came from or why it was released so suddenly. Alternative hypotheses have been proposed, including asteroid impacts and the burning of extensive peat deposits, but none fully resolve the ambiguities. Now consider the possibility, remote but not impossible, that the Paleocene thermal maximum was not caused by natural processes alone. Suppose an industrial civilization had existed in the late Paleocene, a civilization that burned fossil fuels and released isotopically light carbon into the atmosphere. Suppose this civilization grew rapidly, exploiting resources, altering landscapes, and then collapsed, perhaps from environmental degradation or resource depletion or internal conflict. The carbon isotope excursion they created would look very similar to the one we observe. The warming, the ocean acidification, the ecological disruptions, all of these would follow naturally from the addition of greenhouse gases to the atmosphere, regardless of whether the source was industrial or geological. This is not an argument that the Paleocene thermal maximum was caused by an ancient civilization. The natural explanations are adequate, and there is no direct evidence for such a civilization. But the example illustrates a profound point. The signatures of industrial activity, when viewed over millions of years, can be difficult or impossible to distinguish from natural events. A carbon isotope excursion is a carbon isotope excursion. It does not come with a label indicating its cause. Geologists interpret these events based on context, on associated evidence, on what seems most likely given our understanding of Earth's processes. But if the evidence for a civilization, its cities and machines and artifacts, has eroded away, then only the chemical signatures remain, and these are ambiguous. Other events in Earth's history show similar patterns. The Torsion turnover about 183 million years ago was another episode of rapid warming and carbon isotope excursion associated with volcanic eruptions in what is now southern Africa. The end-Permian extinction, the most severe mass extinction in the fossil record, was accompanied by a massive carbon isotope excursion and evidence of widespread anoxia and ocean acidification, possibly triggered by the eruption of the Siberian traps. These events are well studied, and the volcanic explanations are well supported. But the chemical and climatic signatures are remarkably similar to what an industrial collapse might produce. The boundary between natural and artificial becomes blurred when viewed across deep time. The Silurian Hypothesis does not claim that any of these events were caused by ancient civilizations. It simply asks whether we could tell the difference. And the answer, in many cases, is that we could not with certainty. The geological record is too incomplete, too ambiguous, too easily explained by natural processes. This realization has implications that extend far beyond academic curiosity. It touches on fundamental questions about the nature of intelligence, the stability of civilizations, and our place in the cosmos. Consider the fossil record, the archive of ancient life preserved in stone. Fossils are rare. The conditions required for fossilization are specific and seldom met. An organism must die in an environment where it is quickly buried by sediment, protected from scavengers and decay. The sediment must then be preserved, not eroded or destroyed by tectonic activity, and must undergo the chemical transformations that turn soft tissue and bone into mineralized rock. Most organisms do not fossilize. Most species leave no trace. It is estimated that less than 1% of all species that have ever lived on Earth appear in the fossil record. The vast majority vanished without leaving any evidence of their existence. Now consider an intelligent species, one capable of technology and culture, but perhaps not industrial civilization. Such a species might exist for millions of years, spread across continents, develop complex behaviors and social structures, and then go extinct, all without leaving a single fossil that we would recognize as evidence of intelligence. Fossilization favors certain types of organisms, those with hard parts like bones and shells, those that live in environments where sediment accumulates. A species of intelligent terrestrial animals, perhaps tool users or even builders of simple structures, might live and die in environments where fossilization is rare. Forests, for example, are poor environments for fossil preservation. The soil is acidic, rich in organic matter, and bones decay rapidly. If an intelligent species evolved in forests and never developed dense urban centers or large-scale agriculture, it might leave almost no fossil trace. Even humans, despite our current dominance and vast population, may not leave a rich fossil record. Most human remains are not fossilized. Burial practices, cremation, decomposition in environments unsuitable for preservation, all of these factors reduce the likelihood that future paleontologists would find abundant human fossils. If our civilization collapsed today and no further human activity occurred, the fossil record of Homo sapiens millions of years hence might consist of a few scattered bones, mostly from individuals who happen to die in the right places, in caves or riverbeds or lake sediments. The billions of humans alive today will be represented by perhaps a few thousand recognizable fossils, scattered thinly across the geological column. And technology does not fossilize at all. Machines are made of materials that corrode and decay. Computers, vehicles, buildings, infrastructure, all of these would be reduced to unrecognizable debris within a few thousand years and will be completely erased by weathering and erosion over longer timescales. A future paleontologist examining sediment from the Anthropocene might find unusual concentrations of certain elements, might detect anomalies in isotopic ratios, might notice a sudden change in pollen composition indicating deforestation and agriculture. But they would not find intact artifacts. They would not find cities. They would not find machines. The physical evidence of our technology would be gone, leaving only indirect chemical and biological signatures that could be interpreted in multiple ways. This raises an uncomfortable possibility. If intelligence can arise and vanish without leaving unambiguous evidence, then the absence of such evidence tells us nothing about whether it occurred. The argument from absence, the claim that because we see no sign of ancient civilizations, none existed, is invalid. The geological record does not preserve most things. It is biased, incomplete, and easily erased. A dozen industrial civilizations could have risen and fallen in Earth's history, separated by tens or hundreds of millions of years, and we would have no way of knowing. Each would compress into a thin sedimentary layer, a brief chemical anomaly, a subtle shift in isotopic ratios that might be attributed to volcanism or other natural processes. Each would be invisible unless we knew exactly when and where to look, and even then the evidence might be ambiguous. The implications for astrobiology are profound. When we search for life beyond Earth, we look for biosignatures, chemical or atmospheric anomalies that suggest biological activity. When we search for technological civilizations, we look for technosignatures, signs of deliberate manipulation of energy and matter. But if these signatures fade over time, if civilizations are geologically brief, then the probability of detecting them becomes vanishingly small. A planet might host intelligent life, even technological life, many times over its history, and yet appear barren when observed from a distance. The silence of the cosmos, the fact that we detect no radio signals or megastructures or other signs of advanced civilizations, may not mean that such civilizations are rare. It may simply mean that they do not last long, or that they do not leave detectable traces, or that we are not looking in the right way. This line of reasoning leads to a darker interpretation of the Fermi paradox, the question of why we see no evidence of extraterrestrial intelligence despite the apparent abundance of potentially habitable planets. Perhaps civilizations are common, but they are short-lived. Perhaps the transition to industrial technology brings with it inherent instabilities, resource depletion, environmental degradation, internal conflict that make long-term survival unlikely. Perhaps every civilization that discovers fossil fuels follows a similar trajectory: rapid growth, explosive consumption, destabilization of planetary systems, and then collapse or extinction. If this pattern is universal, then the galaxy might be filled with the ghosts of dead civilizations, their planets scarred by brief industrial episodes that have long since faded from the geological record. Earth itself might be such a planet. Not once, but many times. Consider the sheer depth of time available. Complex multicellular life has existed for over 500 million years. Animals with nervous systems, capable of learning and adapting, have existed for nearly as long. For most of this time, the dominant life forms were marine invertebrates, then fish, then amphibians, then reptiles, then mammals and birds. Each of these groups produced species of remarkable complexity and sophistication. Some were social, living in groups and exhibiting cooperative behaviors. Some had large brains relative to their body size. Some used tools or modified their environments in ways that suggest intelligence. But intelligence is difficult to define and even more difficult to detect in the fossil record. We recognize intelligence in living animals through observation of behavior, problem-solving, communication, social structures. Fossils preserve only morphology, the shape of bones, and sometimes traces of soft tissue. Brain size can be estimated from skull volume, but brain size alone does not predict intelligence. Corvids, members of the crow family, are highly intelligent despite having small brains. Octopuses are intelligent despite having brains organized in a radically different way for vertebrates. Intelligence may have evolved multiple times in Earth's history, in lineages that left no clear morphological signature. Imagine, for example, a species of large-brained social reptiles that lived during the Cretaceous period 100 million years ago. They build nests, care for their young, use vocalizations to communicate, perhaps even use simple tools. They live for a few million years and then go extinct, outcompete by other species, or wiped out by environmental changes. Their fossils, if any are preserved, would look unremarkable, indistinguishable from dozens of other reptilian species. We would have no way of knowing they were intelligent. We would interpret them as just another extinct group, interesting perhaps for their anatomy or ecology, but not fundamentally different from other animals. Now take this scenario further. Suppose this species, over the course of its evolution, discovered fire. Suppose they learned to shape stones into tools, to build shelters, to cultivate plants. Suppose they developed a proto-industrial capacity, mining surface deposits of coal or oil, smelting metals, constructing machines. Suppose their civilization lasted 10,000 years, a duration that seems long by human standards but is geologically instantaneous. And then suppose they collapsed, their cities abandoned, their technologies lost, their population crashing back to pre-industrial levels, or going extinct altogether. What would remain? The cities would erode. The machines would rust and crumble. The mines would fill with sediment. The forests would reclaim the cleared land. Within a few tens of thousands of years, the physical landscape would show little sign of their presence. Within a few million years, even the chemical signatures would become ambiguous, mixed with sediments from other sources, diluted by the ongoing geological processes of erosion and deposition. A geologist examining rocks from this period, 100 million years later, might notice a thin layer with unusual properties, elevated carbon levels perhaps, or a strange assemblage of minerals. But would they interpret this as evidence of a civilization? Or would they invoke some natural explanation, a forest fire, a volcanic event, a meteorite impact? Without context, without corroborating evidence from multiple independent sources, the latter interpretation would seem more parsimonious. This is the heart of the Silurian hypothesis. Not that ancient civilizations existed, but that their absence from the geological record does not mean they did not exist. The record is incomplete. The signatures are ambiguous. The timescales involved make detection extraordinarily difficult. And so we are left with uncertainty, a gap in our knowledge that cannot be easily closed. To understand just how incomplete the record is, consider the process of sedimentation itself. Sediments accumulate in specific environments: river deltas, lake bottoms, shallow seas, deep ocean basins. But accumulation is not continuous. Rivers flood and recede. Lakes fill and dry out. Sea levels rise and fall. Each change in environmental conditions alters the pattern of sedimentation. A river delta that is accumulating sediment today might be eroded away tomorrow if the river changes course. A lake that preserves fine layers of sediment for thousands of years might be drained by tectonic uplift, exposing those layers to weathering and destruction. Even in the most stable environments, the deep ocean basins, sedimentation is slow and often interrupted. Sediment accumulates at rates of millimeters to centimeters per thousand years. A civilization that lasts 10,000 years would be represented by a layer perhaps a few centimeters thick, assuming continuous deposition. But deposition is rarely continuous. Currents scour the seafloor, removing sediment. Turbidity flows, underwater avalanches of sediment-laden water, can deposit thick layers instantaneously or erode what was previously there. Bioturbation, the churning of sediment by burrowing organisms, mixes layers together, blurring the boundaries between different time periods. The result is a record full of gaps, unconformities, places where time is missing. Two layers of rock sitting one atop the other might represent time periods separated by millions of years, with everything in between eroded away or never deposited in the first place. Geologists are trained to recognize these gaps, to understand that the rock record is not a continuous narrative but a fragmented collection of snapshots. But this also means that entire chapters of Earth's history are simply absent, unrecorded and unrecoverable. For a brief industrial phase, the chances of preservation are slim. If the civilization existed in a region that was undergoing erosion rather than deposition, no sediments from that time would be preserved. If it existed in a region that was later subducted, the entire record would be destroyed. Even if sediments were deposited and preserved, the specific layer containing evidence of the civilization might never be sampled. Geologists do not drill everywhere or examine every outcrop. They focus on areas of interest, places where rocks are well exposed and accessible, or where there is economic incentive to explore. A thin layer containing anomalous chemistry might be overlooked entirely, dismissed as a minor curiosity not worth detailed investigation. This is not to say that evidence could never be found. If we knew what to look for, if we had reason to suspect that a particular time period might contain evidence of an ancient civilization, we could design studies to test the hypothesis. We could look for multiple independent signatures, carbon isotope excursions, nitrogen isotope anomalies, elevated concentrations of synthetic compounds or refined metals, changes in sediment composition or pollen assemblages that suggest large-scale land use. We could search in multiple locations, trying to find consistent patterns that appear globally rather than just locally. We could use high-resolution techniques to analyze sediments at fine scales, looking for brief spikes or anomalies that might be missed in coarser analyses. But without a specific reason to suspect an ancient civilization, such studies would not be undertaken. The default assumption, the null hypothesis, is that unusual features in the geological record are the result of natural processes. This assumption is reasonable and justified by experience. Natural processes are sufficient to explain the vast majority of geological phenomena. Invoking an ancient civilization to explain a carbon isotope excursion is an extraordinary claim, and extraordinary claims require extraordinary evidence. In the absence of such evidence, the natural explanation prevails, and so we arrive at a paradox. The evidence required to prove the existence of an ancient civilization is unlikely to be preserved or recognized. But the absence of such evidence does not prove that no civilization existed. We are left in a state of irreducible uncertainty, unable to confirm or deny the possibility. This is not a comfortable position for science, which prefers definitive answers and testable hypotheses. But it may be the reality we must accept when dealing with events separated from us by tens or hundreds of millions of years. The implications extend to our own civilization. If we were to vanish today, If some catastrophe or collapse reduced human numbers to pre-industrial levels or drove us to extinction, what would remain? Our cities, our machines, our infrastructure, all of these would decay and erode. The concrete and steel of our buildings would crumble. The plastic in our oceans would break down into smaller and smaller fragments. The carbon dioxide we have added to the atmosphere would gradually be absorbed by the oceans and by the weathering of rocks, returning over hundreds of thousands of years to pre-industrial levels. The radioactive isotopes from nuclear testing would decay. The elevated levels of heavy metals in soils and sediments would be diluted by ongoing geological processes. After 1 million years, the direct physical evidence of human civilization would be sparse. Some materials might persist longer than others. Ceramics, fired clay, are chemically stable and could survive for millions of years if buried in the right conditions. Bronze and other corrosion-resistant alloys might leave recognizable traces. Glass, though it slowly devitrifies and weathers, could persist as distinctive mineral structures. But these would be scattered fragments, rare finds in a vast geological record. A future geologist sampling sediments from our era might find a shard of ceramic or a corroded piece of metal, but would they recognize it as artificial, or would they interpret it as a natural mineral formation? The chemical signatures would be more widespread, but also more ambiguous. The carbon isotope excursion from fossil fuel burning would be detectable, a sudden shift in the carbon-13 to carbon-12 ratio. The nitrogen isotope ratios would also be anomalous, reflecting the massive use of synthetic fertilizers. Concentrations of certain elements, platinum from catalytic converters, lead from leaded gasoline, rare earth elements from electronics, would be elevated in sediments from the mid-20th century onward. These signatures would paint a picture of intense industrial activity, but would they be interpreted as such after millions of years? Or would they be explained by some unknown volcanic event or meteorite impact? The answer depends in part on how thorough the collapse is. If a remnant human population survives and retains some memory of our industrial past, that knowledge might be passed down, eventually leading to the rediscovery of old sites and artifacts. If some structures survive, perhaps deep underground or in particularly stable environments, they might be found and recognized as artificial. But if the collapse is total, if no memory survives, then future intelligence, whether it emerges from our descendants or from some other species, would have to rediscover our existence from the geological record alone. And that record, as we have seen, is fragmentary and ambiguous. This raises a question about the trajectory of industrial civilizations. Is there something inevitable about the pattern of rapid growth followed by collapse? Does the discovery of fossil fuels, those concentrated stores of ancient solar energy, inevitably lead to overconsumption and destabilization? The history of human civilization suggests that it might. For most of our existence, humans lived as hunter-gatherers, their populations limited by the availability of food and resources. The development of agriculture allowed for larger populations and more complex societies, but growth was still slow and often checked by disease, famine, and conflict. The Industrial Revolution, powered by coal and later by oil and natural gas, removed many of these limits. Population exploded. Cities grew. Technology advanced at an unprecedented pace. But this growth was predicated on the consumption of resources that took millions of years to accumulate and that cannot be renewed on human timescales. The fossil fuels we burn today are the remains of plants and plankton that lived during the Carboniferous and other ancient periods, organisms that captured solar energy through photosynthesis and stored it in their tissues. When they died and were buried, that energy was preserved, slowly transformed by heat and pressure into coal, oil, and natural gas. This process took tens to hundreds of millions of years. We are consuming these resources in a matter of centuries. Once they are gone, at least on any timescale relevant to human civilization. A future industrial revolution would have to rely on other energy sources, solar, wind, nuclear, geothermal, or it would not occur at all. This suggests a possible filter, a bottleneck that civilizations must pass through. The first industrial revolution, if it is based on fossil fuels, provides a temporary boost, a surge of energy that enables rapid growth and technological advancement. But it also creates environmental pressures, climate change, pollution, resource depletion that threaten the stability of the civilization. If the civilization can transition to sustainable energy sources before the fossil fuels run out or before the environmental damage becomes catastrophic, it might survive and continue to advance. If it cannot make that transition, it collapses, its population crashes, and it falls back to a pre-industrial state. And because the easily accessible fossil fuels have been consumed, a second industrial revolution becomes much more difficult or impossible. The civilization is trapped, unable to regain the heights it once reached. If this pattern is common, if most civilizations face this same bottleneck, then the galaxy might be full of planets where industrial civilizations rose and fell, each leaving a brief chemical signature in the rock record before vanishing. Some might have made the transition to sustainability and gone on to become space-faring civilizations, but these might be rare. Most might have failed, their planets littered with the faint traces of forgotten industry. Earth might be one such planet, not for the first time, but perhaps for the second or third or 10th time. Each previous civilization would have faced the same challenges, the same temptations and pitfalls. Each would have discovered fire, then agriculture, then the concentrated energy of fossil fuels. Each would have grown rapidly, exploited resources, altered the climate and ecosystems. And each, if it failed to transition to sustainability, would have collapsed and vanished, leaving behind only ambiguous chemical signatures that we, in our own brief moment of industrial power, do not recognize as anything other than natural anomalies. This is speculation, of course. There is no direct evidence for such a scenario. But the absence of evidence is not evidence of absence, especially when the evidence we would need is unlikely to be preserved. The hypothesis is unfalsifiable, at least with the methods currently available to us. We cannot prove that no ancient civilization existed because the geological record is too incomplete to rule out their existence. But neither can we prove that they did exist because the signatures we might look for are ambiguous and could have natural explanations. Some might argue that this makes the hypothesis unscientific, that a claim which cannot be tested is not worth considering. But this misunderstands the purpose of the Silurian hypothesis. It is not a claim, but a question. It is a way of probing the limits of our knowledge, of understanding what we can and cannot learn from the geological record. It forces us to confront the biases and assumptions built into our methods, to recognize that the absence of evidence in a fragmentary record does not constitute strong evidence of absence. And it has practical implications for how we search for life and intelligence elsewhere in the universe. If civilizations leave only brief, ambiguous signatures, then our methods for detecting them must be refined. We cannot rely on finding obvious techno-signatures, radio signals, or megastructures if most civilizations do not last long enough to build such things. We must look for subtler signs, chemical or atmospheric anomalies that might indicate industrial activity, even if those anomalies could also have natural causes. We must accept that ambiguity is inherent in the search, that we may never achieve certainty, but that patterns and probabilities can still guide us. One approach is to look beyond Earth, to places where the geological record is more complete or where preservation conditions are better. The Moon, for example, has no atmosphere and no plate tectonics. Its surface is ancient, with some regions unchanged for billions of years. Craters, rocks, and any artifacts placed there by human or hypothetical non-human visitors would remain largely intact, protected from erosion and weathering. If an ancient civilization on Earth had achieved spaceflight, even briefly, they might have left traces on the Moon that would be far more durable than anything on Earth's surface. This is not as far-fetched as it might sound. Humans reached the Moon only 60 years after the first powered flight. If an ancient civilization had followed a similar technological trajectory, they might have visited the moon during their brief industrial phase. They might have left behind equipment, structures, or other artifacts that would still be visible today. Searches for such artifacts have been proposed, using high-resolution images from lunar orbiters to look for anomalies, geometric patterns, or reflective surfaces that do not match the natural lunar landscape. So far, nothing has been found, but the moon's surface is vast, and only a fraction has been surveyed at high resolution. Mars presents another possibility. Like the moon, Mars has no plate tectonics, and its thin atmosphere means that erosion is slow compared to Earth. Ancient surfaces on Mars are well preserved, with features dating back billions of years. If life arose on Mars and evolved intelligence, or if an Earth-based civilization had visited Mars, evidence might remain. Structures, mines, artifacts, even subtle chemical signatures in the soil could persist for millions or billions of years. The rovers and orbiters currently exploring Mars are not specifically looking for signs of ancient technology, but they are equipped with cameras and spectrometers that could detect anomalies if they encountered them. Some researchers have suggested that certain features on Mars, unusual rock formations, or patterns in the landscape, might be artificial. These claims are generally dismissed by the scientific community, and rightly so, as they typically rely on low-resolution images and pareidolia, the tendency to see patterns and faces in random shapes. But the underlying idea that Mars could preserve evidence of ancient activity better than Earth is sound. If we are serious about searching for ancient civilizations, Mars is a better archive than Earth's surface. Even more intriguing are the icy moons of the outer solar system, worlds like Europa and Enceladus that have subsurface oceans. If life arose in these oceans and evolved intelligence, it might have remained confined beneath the ice, never developing technology beyond what is possible in an aquatic environment. But if such civilizations existed, they might have left traces in the ice or in the plumes of water vapor that erupt from cracks in the surface. These are speculative ideas, far beyond our current ability to test, but they illustrate the breadth of possibilities once we accept that intelligence might arise and vanish without leaving obvious traces. Returning to Earth, we can ask what signatures our own civilization is creating that might be detectable in the distant future. Beyond the chemical and isotopic anomalies already discussed, there are a few more durable markers. One is the presence of novel minerals, compounds created by human activity that do not occur naturally. Concrete, for example, is a mixture of calcium silicates that forms when cement is hydrated. Natural calcium silicate minerals exist, but they have different crystal structures and compositions. Concrete weathers and breaks down over time, but in some environments, it might persist long enough to lithify to become incorporated into sedimentary rocks. A future geologist might recognize these minerals as anomalous and investigate their origin. Another marker is the rearrangement of isotopes by nuclear technology. The isotopic composition of uranium in natural ores is remarkably uniform across the Earth, with a fixed ratio of uranium-235 to uranium-238. But nuclear reactors consume uranium-235 preferentially, altering this ratio. Spent nuclear fuel has a distinctive isotopic signature, one that does not occur naturally, at least not on Earth in the current epoch. If this material is buried and preserved, it could be recognized millions of years later as evidence of artificial nuclear reactions. There is even a natural precedent, the Oklo uranium deposits in Gabon, where natural nuclear chain reactions occurred about 2 billion years ago. The isotopic anomalies there were recognized as evidence of fission, though in that case the reactions were driven by natural geological conditions, not by intelligent activity. Fossilized garbage dumps might also persist. Landfills concentrate materials, plastics, metals, glass, in densities far higher than occur naturally. If a landfill is buried and lithified, it would create a rock layer with highly unusual properties, a chaotic mixture of materials that does not fit any natural sedimentary process. Such a layer would be recognizable as artificial, though interpreting its origin might be challenging without additional context. But even with these markers, the question remains, would they be found? The Earth's surface is vast. The geological record is sparse. A future geologist, even one specifically looking for signs of lost civilization, would have to sample the right rocks from the right time period in the right location. The odds of success are not high. And if the civilization is separated from the search by tens or hundreds of millions of years, the odds decrease further. Time erases. Erosion and subduction and metamorphism grind the record down, mixing and homogenizing and destroying the details that might reveal the presence of intelligence. This brings us to a deeper philosophical point. The Earth does not care about preserving our history. It has no memory, no intention, no awareness. It is a dynamic physical system, driven by heat from its interior and energy from the sun, constantly reworking its surface and interior. The processes that shape the planet operate on timescales that dwarf human lifespans and human civilizations. To the Earth, a civilization is a brief flicker, a momentary perturbation in the carbon cycle, a thin layer of anomalous chemistry that will be diluted and erased by the inexorable grinding of geological time. This perspective is humbling. It reminds us that we are not separate from nature, not above it or outside it, but deeply embedded within it, subject to the same physical laws and processes that govern all matter. Our cities and machines, our art and literature, our hopes and fears, all of these are built from the stuff of the earth, and all of them will return to the earth when we are gone. We are a pattern in the flow of matter and energy, a complex eddy that arose and will dissipate, leaving almost no trace. Some might find this thought depressing, a negation of meaning and purpose. If nothing we do lasts, if even the memory of our existence will fade, then why bother? Why strive? Why create? Why care? But this nihilistic conclusion is not the only response. Another view is that the transience of things makes them more precious, not less. The fact that a sunset lasts only a few minutes does not make it less beautiful. The fact that a civilization lasts only a few thousand years does not make its achievements less remarkable. Meaning and value are not dependent on permanence. They exist in the moment, in the experience, in the relationships and creations that fill the brief span we are given. Moreover, the erasure of history is not total. While the geological record is fragmentary, it does preserve some things. The fossils of ancient organisms, the chemistry of ancient atmospheres, the structure of ancient rocks, all of these tell us about the past, even if they do not tell us everything. Our civilization, too, will leave traces. Future intelligences, if they arise, may find hints of our existence, ambiguous clues that prompt questions and investigations. They may never know our names or our languages or our stories, but they may infer that something happened here, that the planet was altered in ways that suggest deliberate action. And that inference, however uncertain, is a form of memory. There's also the possibility that we ourselves will preserve our own history, not in rocks, but in other media. Digital archives, if maintained and updated, can store vast amounts of information. Physical artifacts, if deliberately curated and protected, can survive longer than natural processes would allow. Space-based archives, placed on the moon or in stable orbits, could persist for millions of years with minimal degradation. These efforts require intentionality and resources, but they are within our capacity. If we choose to, we can create a record that outlasts the geological amnesia of Earth's surface. But such efforts also require that we survive long enough to implement them. And this returns us to the central question of the Silurian Hypothesis. Can industrial civilizations achieve long-term stability, or is collapse inevitable? The evidence from Earth's history is ambiguous. We know of one industrial civilization, our own, and its future is uncertain. We are in the midst of a climate crisis, driven by the same fossil fuel combustion that powered our rise. We face resource depletion, biodiversity loss, social and political instability, all of which threaten our long-term survival. We might succeed in addressing these challenges, transitioning to sustainable practices and stabilizing our impact on the planet. Or we might fail, and the human industrial phase will become another thin layer in the sedimentary record, another ambiguous chemical anomaly for future geologists to puzzle over. If we fail, and if the pattern of rise and collapse is common, then the galaxy might be filled with planets like Earth, worlds where intelligence arises repeatedly only to stumble at the same threshold. Each civilization discovers fire, agriculture, fossil fuels. Each grows rapidly, transforms its world, and then faces the consequences of that transformation. Some might navigate the transition successfully, but many, perhaps most, do not. And because the failures leave almost no trace, the survivors have no way of knowing how many came before them, no way of learning from the mistakes of the past. Each civilization must navigate the crisis alone, reinventing solutions or succumbing to the same traps. This is a lonely vision, a cosmos not empty of intelligence, but full of it, full of brief sparks that flare and die, never connecting, never communicating, each isolated by the vast gulfs of space and time. The Fermi paradox asks where everyone is, why we see no signs of other civilizations despite the apparent abundance of stars and planets. One answer, the Great Filter, suggests that there is some obstacle, some difficult step in the evolution of intelligence or technology that most species fail to pass. The Silurian Hypothesis offers a related but distinct answer. The obstacle is not impassable, but survival beyond it is rare and brief. Civilizações do Arise. They do develop technology, but they do not last long enough to become detectable at interstellar distances. And the evidence of their existence fades quickly, erased by the geological processes of their home worlds. If this is true, then the search for extraterrestrial intelligence must adapt. We cannot expect to find long-lived, stable civilizations broadcasting their presence across the galaxy. We must look for transient signals, brief flashes of activity that might indicate a civilization in its industrial phase. We must examine planets not just for biosignatures, but for technosignatures, and we must accept that these signatures might be subtle and ambiguous, difficult to distinguish from natural phenomena. We must, in short, learn to recognize the patterns that our own civilization is creating to understand what marks we are leaving on our planet, and to search for similar marks elsewhere. This search is just beginning. The first exoplanets were discovered only a few decades ago, and our ability to study their atmospheres and surfaces is still rudimentary. But the pace of progress is rapid. New telescopes, new techniques, new missions are expanding our view of the cosmos and bringing distant worlds into focus. Within the next few decades, we may be able to detect and characterize the atmospheres of dozens or hundreds of Earth-like planets, looking for signs of life and possibly for signs of technology. What would a technosignature look like? It would depend on the nature of the civilization and the stage of its development. A civilization early in its industrial phase might release large amounts of carbon dioxide or methane, creating atmospheric imbalances that we could detect spectroscopically. A more advanced civilization might use chlorofluorocarbons or other synthetic compounds that do not occur naturally and that have distinctive absorption features in the infrared. An even more advanced civilization might build structures visible from space, solar panels covering large areas, reflective surfaces altering the planet's albedo, or even megastructures like Dyson swarms that partially obscure the light of their host star. But if civilizations are typically short-lived, then the probability of catching one in the act of observing a planet at just the moment when technosignatures are present becomes very small. Imagine surveying 100 Earth-like planets. If each planet hosts an industrial civilization for 10,000 years out of a 5 billion-year habitable lifetime, then at any given moment, only about 1 in 500,000 planets would have detectable technosignatures. To find even one, we would need to survey not hundreds but millions of planets, a task far beyond our current capabilities. This calculation assumes that civilizations arise only once per planet, which may not be true. If the pattern of rise and collapse repeats, if intelligence evolves multiple times on the same world, then the probability increases. But even if a planet hosts 10 or 100 separate industrial phases over its history, the total duration of detectability might still be only a few million years out of billions, a tiny fraction of the planet's lifetime. The chances of catching a technosignature during a brief observation are correspondingly small. These considerations suggest that the search for technosignatures, while worthwhile, may require patience and scale. We may need to observe thousands or tens of thousands of planets before finding one with unambiguous signs of technology. And even then, the signal might be ambiguous, explainable by natural processes, requiring additional observations and analysis to confirm. The search will be slow, uncertain, and frustrating, but it is also one of the most profound questions we can ask. Are we alone, or have others walked the path we are now walking? Returning once more to Earth, we can reflect on what the Silurian Hypothesis teaches us about our own moment in history. We are living through a unique time, the first decades of an industrial civilization that has achieved global reach and impact. We have transformed the planet in ways that will be visible in the geological record, assuming that record is preserved. We have split the atom, synthesized novel compounds, altered the composition of the atmosphere and oceans, driven species to extinction, and reshaped landscapes on a continental scale. All of this has happened in the span of a few human lifetimes, a geological instant. But we do not know whether this transformation is sustainable. We do not know whether we can stabilize our impact, transition to renewable energy, reduce our consumption of resources, and coexist with the other species that share this planet. We do not know whether human civilization will endure for millennia or collapse within centuries. We are, in a sense, conducting an experiment, testing the hypothesis that intelligence and technology can lead to long-term stability rather than self-destruction. The outcome is not yet determined. We have the capacity to succeed, but success is not guaranteed. The Silurian Hypothesis suggests that if we fail, we will not be the first. Other intelligences may have arisen on this planet before us, may have faced similar challenges, and may have failed in similar ways. Their failure did not prevent the evolution of new species, new ecosystems, new opportunities for intelligence to arise. Life continued, the planet continued, and eventually we emerged, unaware of what had come before, repeating the same experiment. This perspective does not absolve us of responsibility. Even if collapse is survivable at the planetary scale, it is not survivable for the individuals and communities who experience it. Civilizations are made of people, and when civilizations collapse, people suffer. The abstract fact that the planet will recover and that life will continue is no comfort to those who are displaced, starved, or killed by environmental catastrophe. Our responsibility is not to the distant future or to the geological record, but to each other, to the present and near future generations who will inherit the consequences of our actions. Nor does the possibility of prior civilizations make our achievements less significant. If intelligence has arisen before, if technology has been discovered and lost and rediscovered, that does not diminish what we have accomplished. Each instance of intelligence is unique. Each civilization creates its own meanings and values, its own art and science and philosophy. The fact that others may have done something similar does not make our efforts redundant or meaningless. It simply places us in a broader context, part of a pattern that may be common in the universe, a pattern of striving and creating and questioning that defines what it means to be intelligent. The haunting quality of the Silurian Hypothesis lies not in its claims, for it makes none, but in its questions. It asks us to imagine deep time, to confront the reality that most of history is lost and unknowable, to accept that we may never achieve certainty about the past or the future. It asks us to consider that we might be repeating an ancient pattern, rising and falling like others before us, our achievements and failures compressed into a thin sedimentary layer that will fade and be forgotten. It asks us to hold two contradictory thoughts simultaneously: that we are unique, the only technological civilization we know of, and that we may be one of many, our story echoing those that came before and that will come after. This duality is uncomfortable. Humans crave narratives with clear beginnings and endings, heroes and villains, progress and resolution. The Silurian Hypothesis offers no such narrative. It offers only ambiguity, uncertainty, and the vastness of time. It reminds us that the universe is not structured to provide us with answers, that some questions may be unanswerable, and that we must learn to live with doubt. But there is also something liberating in this uncertainty. If the past is unknowable and the future is undetermined, then we are not bound by precedent or destiny. We are free to choose, to experiment, to create new possibilities that may not have existed before. The fact that previous civilizations, if they existed, may have failed does not mean that we must fail. We can learn from our own mistakes, adapt to changing conditions, and build institutions and technologies that promote stability rather than collapse. The path is not predetermined. The outcome depends on the choices we make. And so we return to the present moment, to the thin layer of sediment currently accumulating on Earth's surface, the layer that contains the traces of our existence. This layer is still being written. Its composition, its chemistry, its ultimate thickness and preservation, all of these depend on what we do in the coming decades and centuries. We have the power to shape the legacy we leave, not by building monuments that will erode or writing text that will decay, but by stabilizing our relationship with the planet, by creating systems that can endure, by fostering knowledge and memory that can be passed to future generations. Whether we succeed or fail, the layer will be there, a thin dark line in the sedimentary column, a marker of a time when one species briefly dominated the planet and then, one way or another, released its grip. Future geologists, if they exist, may find this layer and wonder about it. They may analyze its chemistry, its isotopes, its mineral content, and debate what natural or artificial processes could have created such anomalies. They may never reach a definitive answer. The evidence may remain ambiguous, open to interpretation. But perhaps that ambiguity is appropriate. Perhaps it is fitting that the record of intelligence should be uncertain, that the question of whether we are first or merely latest should remain open. The universe is vast and old, far vaster and older than our minds can fully grasp. The Earth alone has existed for 4.5 billion years, a span of time so immense that the entire history of human civilization is a rounding error, a statistical noise, a flicker at the very end. To imagine that we are the first intelligence to emerge in all that time, on a planet that has hosted complex life for over 500 million years, requires a certain arrogance, a belief that we are special, chosen, unique in a way that the laws of probability do not support. But to imagine that others came before us, that intelligence has risen and fallen repeatedly, requires a different kind of humility, an acceptance that we're not the culmination of history, but merely a step in an ongoing process, one that may have repeated many times and may repeat again. This humility is difficult. It challenges our sense of importance, our belief that what we do matters in some cosmic sense. But it is also honest. It aligns with what we know about the universe, about the transience of all things, about the grinding indifference of geological and cosmic processes. The Silurian Hypothesis does not tell us whether ancient civilizations existed. It tells us that we cannot know, that the methods available to us are insufficient to answer the question with certainty. It tells us that the absence of evidence is not evidence of absence, that the silence of the rocks does not mean that nothing happened. It tells us that the universe is full of mysteries we may never solve, questions we may never answer, and that this is not a failure of science, but a recognition of its limits. In the end, we are left with a simple and profound realization. The Earth is old. Life is persistent. Intelligence may be more common than we think, arising whenever conditions permit, only to vanish when those conditions change. Our own civilization is a brief experiment, an attempt by one species to reshape its world and extend its reach beyond the limits imposed by biology. We do not know if the experiment will succeed. We do not know how long we will last or what we will become. We do not know if others tried before us or what lessons they might have learned. What we do know is that we are here now, conscious and curious, capable of asking questions that span millions of years and billions of miles. We can look at the rocks beneath our feet and read in them the history of ancient seas and forests and climates. We can look at the stars above and imagine worlds circling them, worlds that might be or might have been home to other minds. We can contemplate our place in the vast tapestry of time and matter, recognizing both our insignificance and our uniqueness. And we can choose within the narrow window of opportunity we have been given to act with intention and care, to build a civilization that endures, to leave a legacy that is not merely a chemical anomaly in the rock record, but a living, evolving culture that continues to ask questions, to explore, to create. Whether we're the first to attempt this or the latest in a long series of attempts, the effort is worthwhile. The outcome is uncertain, as it has always been, as it always will be. The earth turns, the continents drift, the mountains rise and erode, the oceans circulate. Life continues, adapting to whatever conditions prevail, indifferent to the ambitions and failures of any single species. Deep time stretches out in both directions, past and future, an immensity that dwarfs our brief moment of awareness. We are a pattern in the flow, a temporary complexity, a question mark written in stone and carbon and memory. And the stone forgets. The carbon cycles. The memory fades. But while we remain, we can wonder. We can ask. We can imagine what came before and what might come after. We can hold in our minds the possibility that the silence of the rocks is not proof of emptiness, but of forgetting, that the earth has secrets it no longer remembers, stories it has erased, civilizations it has buried and crushed and recycled into new forms. We stand on ground that might have been walked by others, though we will never know their names or see their faces or read their writings. We breathe air that carries the faintest trace of their industries, diluted and dispersed and mixed with the exhalations of volcanoes and forests and oceans. We are separated from them, if they existed, by an abyss of time so profound that even the rocks cannot bridge it, can offer only hints and shadows and ambiguities. This is the lesson of the Silurian Hypothesis. Not that ancient civilizations existed, but that their existence is possible, that the geological record is too fragmentary to rule it out, that we live in uncertainty and must accept it. Not that we are unimportant, but that importance is not measured in geological persistence. That meaning is found in the moment and the experience rather than in the permanence of artifacts. Not that our efforts are futile, but that their value lies in themselves, in the striving and creating and questioning, not in the distant echoes they might leave. The night deepens. The stars turn overhead, distant suns whose light has traveled for years or centuries or millennia to reach us. Around some of those stars, planets orbit, worlds we will never visit but can study from afar. Some of those worlds might harbor life. Some might harbor intelligence. Some might, at this very moment, be hosting civilizations grappling with the same questions we face, wondering if they're alone, wondering if others came before them, wondering if the silence of their own rocks means anything. And perhaps, on some of those worlds, the question has already been answered. Perhaps some civilizations have found unambiguous evidence of their predecessors, artifacts or messages or structures that survive the grinding of time. Perhaps they have learned from those predecessors, avoided the mistakes that led to collapse, built societies that endure for millions of years instead of thousands. Perhaps they have spread beyond their home worlds, established archives on moons and asteroids, ensured that their existence will never be forgotten. Or perhaps they have not. Perhaps they, too, struggle with fragmentary evidence and ambiguous signals. Perhaps they, too, wondered and questioned and never found certainty. Perhaps the universe is full of such civilizations, each isolated by time and space, each asking the same questions, each receiving the same silence in response. We cannot know. The distances are too great, the timescales too long, the signals too faint. We can only continue to search, to observe, to analyze, to imagine. We can only build our own civilization, make our own choices, create our own legacy, whatever form it may take. We can only accept that we are embedded in deep time, that our moment is brief, that the planet will outlast us and forget us, and that this is simply the nature of existence on a dynamic, living world. The hypothesis stands not as an answer, but as a reminder that the past is vast and mostly unknowable. A reminder that absence of evidence is not evidence of absence, especially when the evidence we seek is unlikely to be preserved. A reminder that the Earth is old and has witnessed things we will never see, events we will never reconstruct, stories we will never hear. A reminder that we are not separate from nature, but part of it, subject to the same forces and processes that shape all matter, all life, all complexity. And a reminder that this is enough. That our brief moment of consciousness, our capacity to wonder and question and create, has value regardless of how long it lasts or what traces it leaves. That the meaning we make is real, even if it is temporary. That the connections we forge, the knowledge we accumulate, the beauty we create, all of these matter, not because they will endure forever, but because they exist now, in this moment, in the thin slice of time we call the present. The Earth continues its orbit. The sun continues to burn. The galaxy continues to spiral. And somewhere in a thin layer of sediment accumulating on the ocean floor, in the isotopic composition of carbonates forming in warm seas, in the subtle chemistry of soils and ice cores and lake beds, the story of our civilization is being written, not in words, but in elements and isotopes and molecules. Not as a narrative with heroes and villains, but as a set of chemical anomalies, changes in composition and concentration that deviate from the background, that suggest something unusual happened during this particular sliver of geological time. Future investigators, if they arise, will find these anomalies or they will not. They will interpret them correctly or they will not. They will understand that an intelligent species once altered this planet, or they will attribute the changes to volcanism, to orbital variations, to asteroid impacts, to any of the myriad natural processes that can mimic the effects of industry. The record will be ambiguous. The evidence will be incomplete. The conclusion will be uncertain. And perhaps that is how it should be. Perhaps the universe is not designed to provide us with clear answers, with definitive proof of our uniqueness or our commonality. Perhaps it offers only questions, mysteries, invitations to explore and imagine and wonder. Perhaps the search for ancient civilizations, whether on Earth or on distant worlds, is valuable not because it will yield certain knowledge, but because it expands our perspective, challenges our assumptions, and reminds us of the vastness and strangeness of the cosmos we inhabit. The silence of the rocks is not proof of emptiness. It is simply silence. And in that silence, we can hear echoes, real or imagined, of other voices, other minds, other moments of consciousness that flickered briefly in the long night of time. We can wonder if they were like us, if they faced the same challenges, if they succeeded or failed, or simply vanished without resolution. We can recognize that we may never know, that some questions remain forever open. That uncertainty is not a flaw in our understanding, but an inherent feature of reality. This is the haunting that the Silurian Hypothesis invokes. Not the ghost of a specific lost civilization, but the recognition that ghosts might exist, that history might contain chapters we cannot read, that the planet beneath our feet might hold secrets it will never reveal. It is a haunting without form or substance, a presence felt only through absence, a story told only through gaps and silence. And yet, even in this uncertainty, there's a kind of comfort. If intelligence has arisen before, if it might arise again, then we are part of a larger pattern, a process that transcends any individual species or civilization. The impulse to know, to understand, to manipulate the environment, to create tools and art and meaning. This impulse might be woven into the fabric of life itself, emerging whenever conditions permit, persisting as long as conditions allow, fading when conditions change, but never entirely extinguished. Life is resilient. It adapts. It survives mass extinctions and climate shifts and asteroid impacts. It colonizes new environments, evolves new forms, explores new possibilities. Intelligence, as a product of life, inherits this resilience. It is not guaranteed to survive any particular crisis, but as a phenomenon, as a potentiality, it may be nearly indestructible. Knock it down, and it may rise again. Erase its memory, and it may rediscover what was lost. Bury its artifacts, and it may build new ones. This is not a claim of inevitability. Evolution does not have goals or destinations. Intelligence is not the pinnacle toward which life strives, but one option among many, one strategy for survival and reproduction. Many species thrive without it. Many ecosystems function without a single intelligent member. But the capacity for intelligence exists within the genetic potential of life, and given enough time and enough opportunities, it may emerge repeatedly. If this is true, then the Silurian hypothesis takes on a different quality. It becomes not a question about whether one or two ancient civilizations existed, but a recognition that the Earth might be an engine for generating intelligence, that over the vast span of geological time, consciousness might have flickered into existence many times, each instance unique, each unaware of the others, each asking the same fundamental questions about existence and meaning and purpose. We are perhaps one such flicker, bright, brief, intense, and ultimately transient. Our light will fade, as all lights do. But while it burns, it illuminates something, reveals something, creates something. And that something, however temporary, is not nothing. It is a moment of the universe becoming aware of itself, a localized increase in complexity and order, a pattern that asks questions and seeks answers even though the answers may not exist or may be forever out of reach. The geological record will compress our moment into a thin line, a subtle shift in chemistry and isotopes. Future geologists, if they exist, may notice it or may overlook it. They may interpret it correctly or may explain it away. But the moment will have existed. We will have existed. And that existence, however brief and however forgotten, is its own justification, its own meaning. There is no moral to this story, no lesson to be drawn, no warning or call to action. There is only the story itself, the unfolding of time, the rise and fall of complexity, the cycling of matter and energy through forms that briefly cohere and then dissolve. We are part of this cycling. We always have been. We always will be. And the planet, indifferent and eternal, will continue to turn, to change, to evolve, to erase its own history and write new stories in stone and ice and bone. Deep time stretches out in all directions. The past is vast and mostly dark, illuminated only by scattered fragments, fossils and rocks and isotopes that hint at what once was. The future is vast and entirely dark, unknowable, open to infinite possibilities. We occupy a single point, a single moment, a single breath in the long exhalation of the cosmos. And in this moment, we can choose to be curious, to ask questions, to seek understanding even when understanding is incomplete. We can choose to create, to build, to connect with others, to forge meaning out of the raw material of existence. We can choose to care for the planet and for each other, not because doing so will ensure our immortality, but because it is the right thing to do, the humane thing, the thing that makes our brief moment more bearable and more beautiful. The Silurian hypothesis asks us to imagine what we might never know, and in doing so, it invites us to embrace uncertainty, to accept the limits of knowledge, to find peace in the questions rather than demanding answers. It invites us to see ourselves not as the center of history, but as a part of it, one thread in a vast and complex tapestry that extends far beyond our vision. The night deepens. The silence deepens. And somewhere in the accumulated sediments of ancient seas, in the chemistry of rocks formed millions of years ago, in the structure of crystals and the ratios of isotopes, there may be traces faint and ambiguous of others who came before. Or there may be nothing. We will likely never know. And perhaps that not knowing is itself a form of knowledge, a recognition that the universe is larger and stranger and more mysterious than we can ever fully comprehend. We are here. We are conscious. We are asking questions. And that, in the end, may be all that matters. Not the answers we find or fail to find. Not the legacy we leave or fail to leave. But the asking itself, the reaching out into the darkness, the attempt to understand and connect and create meaning in a cosmos that offers no guarantees, no assurances, no promises. The earth turns, the stars burn, time flows, and we, for this brief moment, are awake, aware, alive. We stand on ground that is ancient beyond measure, beneath a sky that contains more stars than we will ever count, in a universe that is vast and indifferent and filled with possibilities we can barely imagine. We are alone, or we are not alone. We are first, or we are one of many. We will endure, or we will vanish like smoke in the wind. And the uncertainty, the not knowing, the endless questioning is what it means to be human, to be intelligent, to be conscious, to be a pattern in the flow that asks why, that wonders what, that seeks to understand even when understanding is impossible. The hypothesis stands, not proven, not disproven, but present, a question mark etched into the foundations of our knowledge. The rocks are silent. The isotopes are ambiguous. The evidence is absent or explained away. And we are left with wonder, with imagination, with the haunting possibility that we are walking in footsteps we cannot see, repeating patterns we do not remember, writing a chapter in a book whose previous pages have been torn away. This is where the story rests, not in conclusion, but in continuation, not in certainty, but in doubt, not in noise, but in silence, the kind of silence that invites listening, the kind of darkness that invites seeing, the kind of emptiness that invites filling, or perhaps simply accepting. Deep time surrounds us. We float in it, suspended between unimaginable past and unknowable future, a mode of consciousness in an ocean of matter. And the ocean does not notice us. It does not care. It simply is, was, and will be, churning and cycling and transforming, indifferent to the brief sparks of awareness that arise and fade within it. And yet, those sparks are not nothing. They are something. They are us. And while we burn, we illuminate something real, something meaningful, something that matters to us, even if it matters to nothing else. The planet will forget us. But we are here now, and now is all we have ever had, all we will ever have. The rest is silence. The rest is time. The rest is the slow grinding of stone against stone, the patient work of erosion and uplift, the eternal return of matter to its elemental forms. The rest is the deep, abiding, eternal forgetting that is the earth's only memory. And in that forgetting, there's a kind of peace, a release from the burden of permanence, from the demand that we leave a mark that lasts forever. We can create for the moment, for the experience, for the joy or meaning it brings now, without needing it to echo through eternity. We can accept our transience and find freedom in it. The hypothesis does not demand belief. It does not insist on ancient civilizations or lost empires. It simply opens a door, reveals a possibility, asks us to consider that the silence might be full of unspoken stories, that absence might not mean what we think it means, that the limits of detection might be more profound than the limits of existence. And through that door, if we choose to walk through it, we find not answers but more questions. Not certainty, but deeper uncertainty. Not comfort, but a strange, austere beauty in the recognition of how little we know and how much we will never know. This is the final resting place of the thought, not in resolution, but in resonance. not in a conclusion, but in an opening, not in a statement, but in a question that lingers, unanswered and perhaps unanswerable, echoing through the vast halls of time. We are here. Others may have been here. Still others may come. The planet does not distinguish between us. It records what it records, forgets what it forgets, continues regardless. And we, for our part, continue to wonder, to question, to imagine, to exist briefly in a narrow band of time where matter becomes mind and asks why. The silence is not empty. It is full of everything we cannot hear, full of everything we have forgotten, full of everything we will never know. And in that fullness, there is a kind of completion, not of knowledge, but of perspective, not of understanding, but of acceptance. The earth is old. Intelligence may be a recurring dream it has, waking briefly, asking questions, then dissolving back into the geology from which it arose. We are perhaps the current dream. And when we fade, the planet will sleep again, untroubled, unchanged, waiting for the next awakening. Or for none at all. It does not matter to the earth, but matters to us. And that is enough.